A proper acronym for cross-site scripting is XSS, as CSS is already reserved for cascading style sheets. Anyway, this attack used to be extremely popular in the past. It's still very widespread. XSS relies on the fact that most websites are active to some degree. Websites display information and also allow users to post some information as well. Since a two-way communication is available, we can use this to place something on an external website. We can run the following attack. First, we'd like to embed a malicious script on a website. It can be embedded directly on the site. In the easiest case, the site will have a comment box. This can be exploited to leave HTML tags next to a comment so that the script is created. After this is done, we wait for a visitor to display the site. Once it's displayed, a browser will render the entirety of the page, including our script. The script payload is up to us. Script can be embedded on a website or placed inside a link to a page that is sent to the victim. This variation is the basis for the division of cross-site scripting attacks into two types: reflected XSS and persistent XSS. A reflected XSS attack occurs when an attacker communicates with the victim directly. We'll see an example of this attack in a moment. We can, for example, be persuaded to click on the following address. Although we're connected to a bank page, we also launched a script that is not stored in the page. The bank website is not compromised. It has not been broken into. It's our session that is no longer secure. This attack can be delivered in a number of ways. We can, for example, be redirected to a different page without noticing it. We can also launch a script on a trusted page that comes from a different page. A persistent cross-site scripting attack, on the other hand, relies on placing malicious code directly onto a website instead of putting it in a link, for example, in an email. This type of attack is definitely easier to detect. It's also larger in scale. Let's see how this works in practice. Assume you've received the following email message. This message doesn't look too suspicious. You can see that it was sent from a bank branch. There are no mistakes in language. The message reads unambiguous and doesn't seem to raise any doubts. The email doesn't ask you for your login or password or pressure you to log in the next 35 seconds to get a prize. There's no such tactics in this message. All it asks you is to click on a link to log in. As you can plainly see in the status bar of the browser, a hidden longer address lurks underneath the link. It's longer than expected. Anyway, we still click it. We are redirected to a login page of the bank. It looks familiar. The page looks no different than it looked before. Everything seems in perfect order, until you take a look at the address bar. It turns out that while the bank page is displayed on the screen, a script is running at the same time. To get a better picture of the situation, we can copy the script into a notepad. The script here is not contained in the bank page. It's a JavaScript called Snoop. We can assume that the script will be executed soon because we can see an event that launches it. Assume that we haven't caught all this and decided to log in. After clicking a logging link, there's a window that looks normal. But after submitting login and password, something strange pops up. The right side was never originally part of the window. Actually, even now it's not visible. The script we show simply aims to demonstrate that an attacker has access to the credentials we submit. If correct credentials are submitted, we logged in correctly. There's one problem though. We've just fallen victim to a cross-site scripting attack. Despite the fact that we're connected to a trusted and unmodified page, we have connected to it in such a way that the location of the script that will be executed by us in a moment was also sent. The script is contained on a server controlled by a black hat hacker. This type of attack can be thwarted quite easily, even using automated tools. Note that when you click on the link in the email again, the browser prompts a message stating that it's modified the page's source code. This time, a logging attempt doesn't cause any adverse side effects. The browser detected that the page's code contains links to scripts stored on external servers under different addresses. It commented them out before interpreting the code. Below you can see a script that was executed on this page. It aims simply to read the values of user-supplied login and password fields. The last topic we'll briefly cover relates to session hijacking. Session hijacking is an event of impersonating a user that has been authenticated to an application. It doesn't involve cracking or guessing a user's password. An attacker waits for a user to log on and logs as well along that user. This attack scenario is in particular a threat to web applications, especially since many of them use HTTP. Since HTTP is a stateless protocol, it has to simulate a session in some manner. A session is simulated in this case by the advent of adding identification data to each query. The data in question could be cookies or other data placed inside URI addresses. This means that a cookie, an unprotected text file, is a temporary credential. If someone obtains our cookie, that person can impersonate us in the application. If we've been previously authenticated to that application, the hijacker will also be authenticated. We see a Wireshark session where an HTTP cookie has just been intercepted. This, however, can be done easier, even without resorting to Wireshark. A Firefox add-on such as Firesheep can be used for this purpose. The extension works just like Wireshark. It listens on for users transmitting cookies to a selected array of websites. If an exchange is detected, the sniffer steals the cookie and shares the use of the cookie with the legitimate user. A server is not alarmed if someone sends more than one copy of a cookie. To pull the attack off, an attacker needs only to share a medium with the targeted user. This is viable, for example, in an internet cafe. What methods can be engaged to foil session hijacking? It's possible to bind a session identifier to something that identifies a user uniquely. For example, bind a session identifier to computer data, a MAC address or an IP address. This produces one problem. Using Wi-Fi networks, we sometimes switch between various access points. Computer configuration can change during this process, and losing a session needs to be avoided, for example, because we're in the middle of some important operation. This solution is quite intrusive. An alternative is encrypting all traffic using HTTPS. This encryption would also make a cookie encrypted. Extracting cookies from packets would no longer be possible. This module discussed typical application attacks. The major focus was placed on database servers since most applications today make use of them even if you're not aware of it. Other than that, buffer overflow attacks were covered as well as cross-site scripting. Both of these attacks target website visitors and not websites. At the end, authenticated session hijacking information was proposed to sum up the topic. Thank you.